So in this video we're going to have a look at ideal gas laws, and by the end you should be able to use ideal gas law relationships and know the constants associated with the equations. Now, the ideal gas laws are used in a variety of different subjects. We use them in physics, they get used in chemistry and statistical mechanics, just as a few examples. And because they're used in so many different fields, sometimes one equation is more useful than another equation. There are two common forms of the ideal gas law, and you might have seen these before. And these are PV equals nRT and PV equals nKT. You'll want both of these in your notes, but we'll go through what all of the variables mean, so maybe hold off for a moment on putting these in your notes. So the first one that we mentioned there, PV equals nRT, and this one's really common in chemistry. That lowercase p is the pressure in pascals. Some textbooks you see it as an uppercase p, but your exam we use a lowercase p. V is the volume in cubic meters. N is the number of moles. R is the molar gas constant, and that is given on your data sheet. It's just 8.31 joules per Kelvin per mole. And T is the temperature in Kelvin. Now there are a few things that we need to be careful of, namely units. For the volume, being cubic meters, we need to be careful with any conversions that we're given, because 1 cubic meter is like having a meter stick by meter stick by meter stick. It's absolutely massive. So we've got 1 meter by 1 meter by 1 meter. But each of those meters is 100 centimeters. So if we were to calculate 1 meter cubed, that's like saying 1 meter times 1 meter times 1 meter. But each of those meters is worth 100 centimeters. Which means 1 cubic meter is actually 1,000,000 cubic centimeters. So we do need to be careful with that conversion, that we're not just doing a factor of 100 or even a factor of 1,000 or 10,000. It is a factor of 1,000,000. The other thing that we have to be careful of is that the temperature is measured in Kelvin. Now this is not a change in temperature, this is the absolute temperature. So we cannot use degrees Celsius here because we are looking at absolute temperature. When this temperature is 0, something over here, either the pressure or the volume, must be 0. We cannot have a negative temperature because we cannot have a negative pressure, we cannot have a negative volume, we cannot have a negative number of moles, and this constant is positive. So we cannot use a negative temperature inside this equation because there's nothing else that's negative inside there, and we'd end up with a positive number equals a negative number, which makes literally no sense mathematically. And this is why it's so important that we have that absolute 0. And this is why Lord Kelvin was really advocating for having an absolute 0. So a 0 temperature when we have a 0 pressure. I'd recommend now pausing the video so that you can get that ideal gas law into your notes, making sure that you highlight to be careful with a volume in cubic meters and a temperature in Kelvin. And this is the other form of our ideal gas law, PV equals nKT. Now that lowercase p is still pressure in pascals, that V is still volume in cubic meters. We still have the same worry there about making sure we get cubic meters converted correctly. And that T is still the temperature in Kelvin, again being careful that it has to be in Kelvin and not in degrees Celsius. This capital N is different from our lowercase n in our previous equation, and capital N is the number of particles. Now in most cases that's going to be the number of molecules, so if we take air for example, the number of particles will contain like the N2, the O2, the argon, the carbon dioxide, so those would be considered molecules. Whereas if we have, say, helium gas, those would be monatomic gas, where those particles are going to reference just the singular helium atom. And then K is a different constant. It's the Boltzmann constant, 1.38 times 10 to the minus 23 joules per Kelvin, and this is given on your data sheet. So now would be a good time to pause the video and write down what you'd like for this ideal gas law. So you can derive these laws from molecular kinetic theory, which we'll do in a subsequent lesson. And that derivation was actually done independently by two different people, one in 1856 and one in 1857. But that is not actually how we have these ideal gas laws. So that derivation is something that we were able to mathematically do after the fact, but not how we came up with these gas laws. So about 20 years before molecular kinetic theory, Emile Clapeyron stated the ideal gas laws. And he stated that they're a combination of Boyle's law, Charles' law, and Avogadro's law. Now we'll go through these three laws in a moment, but all three of these are completely experimentally derived laws. And that's a really important aspect, that it's completely experimentally. So I absolutely love doing derivations, mathematical derivations, but this is not mathematically derived. It was completely done experimentally. So these three gas laws, Boyle's law, Charles' law, and Avogadro's law, and the ideal gas law in both of its forms, are empirical in nature. And your exam really wants to get, or your exam board I should say, really wants to get this idea across that the ideal gas laws are derived experimentally, and then molecular kinetic theory is derived with mathematics, and that the two agree with each other, which gives us a big hint that they're probably along the right track if we have completely experimental derivation and a completely mathematical derivation coming together and being the exact same thing. So Boyle's law is an experimentally derived gas law that states pressure is inversely proportional to the volume of a gas for a constant mass at a constant temperature. And I would like you to write an expression to show pressure is inversely proportional to the volume of a gas. Pause the video now and have a go at that. So your expression should look something like this. Pressure is inversely proportional to volume. Or you might have something like this, where pressure times volume is a constant. This law was published in 1662 by Robert Boyle, but this relationship was first noted by Richard Towneley and Harry Power. Boyle just confirmed their discovery through experiments. He had an assistant to do the experiments with, and the experimental apparatus was built by his assistant, Robert Hooke. Yes, that is Hooke's law Hooke. But independently of Boyle and Hooke, I don't know how to say the first name, Edmy Marriott, a French physicist and priest, also discovered the pressure-volume relationship of a gas in 1679. And now you might say, like, how can you do that independently and, over a decade later? That's 17 years later. But back in the 1600s, communication wasn't what it is today. So it is viewed as they did it independently. So sometimes, even though Boyle was the first one to publish it, sometimes it's called the Marriott's law, or the Boyle-Marriott law. So if you're looking at other sources, it might be called something else. For your exam, you need to know it as Boyle's law, and you need to know that Boyle's law references pressure and volume relationship. So how you want to put that in your notes, completely up to you. Charles' law is an experimentally derived gas law stating that the volume of a gas is proportional to the temperature of a gas for a constant mass at a constant pressure. So I'd like you to have a go at writing this out mathematically. Pause the video now and give that a try. So you should have something along the lines of volume is proportional to temperature, or that volume divided by temperature is equal to a constant. And the history of this law is even more bizarre than Boyle's law. So scientists describe the basic principles that volume is proportional to temperature about a century before it's published. So in 1708, Francis Hauksbee, which is actually Isaac Newton's lab assistant, discovered that the volume of a given mass of a gas is proportional to its temperature at a constant pressure. And actually, even before him, I'm going to say this name incorrectly because I don't know how to pronounce it, but I'll give it a go. Guillaume Amontons made similar conclusions. In 1801, John Dalton, who's an English chemist, physicist, meteorologist, and responsible for our idea of an element, he published a number of essays on his work with gases, and he showed that all gases and vapours he studied expanded by the same amount between two fixed temperatures. So that shows a volume-temperature relationship. A few months later, at the beginning of 1802, Joseph Louis Gay-Lussac, a French chemist and physicist, confirmed the discovery in a presentation to the French National Institute. So you might have heard this called the Gay-Lussac law, and that's after him. Despite everyone else's work, Gay-Lussac credited the discovery to the 1780s unpublished work of a fellow Frenchman, Jacques Charles. And really, it's just from his lab notes that Gay-Lussac went, you know what, I got all my ideas from Jacques Charles. We should name this after him because he kept such a great lab book. So really important to keep great lab notes. In terms of what you need for your exam, make sure that you know Charles's law is a relationship between volume and temperature. And while it is called the Gay-Lussac law in other literature, the only way that your exam will refer to it is Charles's law. And the last one is Avogadro's law. It's an experimentally derived gas law stating that the volume of a gas is proportional to the amount of substance of a gas at constant pressure and temperature. So pause the video and take a moment to write that out mathematically. So we should have that volume is proportional to N, which is our number of moles, which is the amount of substance of a gas. Or you could have written it as V divided by N is a constant. Now the history behind this one is even more bizarre. So in 1811, Italian chemist Amedeo Avogadro hypothesized that equal volumes of all gases at the same temperature and pressure contain equal numbers of molecules. That implies that the ratio of the molecular weights of any two gases is the same as the ratio of the densities of the gases. We aren't going to in this video, but if you'd like a bit of a challenge, you can make that conclusion from one of the other ideal gas laws. And from that, Avogadro reasoned that gases were not made up of singular atoms. And that was the common thought at the time, that a gas was singular atoms. And Avogadro said, actually, instead of singular atoms, they're made up from compounds of two or more atoms. And now we know that some gases are made up of single atoms, like argon and all of the noble gases. But most of the gases that scientists use, like nitrogen, oxygen, hydrogen, are diatomic molecules. So each molecule contains two atoms. Nitrogen has two nitrogen atoms, oxygen two oxygen atoms, hydrogen two hydrogen atoms. Despite him being correct, his work was just pretty well ignored. Part of the reason is probably because he was based in Italy. So in the 1800s, the centres of chemistry were France, Germany, England, and Sweden, which are a long way from Italy in an era of steam-powered vehicles. And possibly a larger part of the reason that he was ignored was the popularity and what was deemed common knowledge. So popular scientists like, I don't know how to say his first name, Berzelius, and our aforementioned English chemist John Dalton, they'd previously developed theories that disagreed with Avogadro's work. Like, Berzelius claimed that compounds are held together by the attraction of positive and negative electrical charges, and Dalton theorized that all atoms in a given element are identical in mass and properties. So it would be inconceivable to have a molecule composed of two like atoms, like in nitrogen gas, and it would be absolutely ludicrous to even suggest this. In 1860, which was 4 years after Avogadro's death, Cannizzaro presented Avogadro's work at a conference specifically called to fix scientific confusion regarding atoms, molecules, and their masses. And Cannizzaro continued to advocate for Avogadro's work for another decade or so, before it was finally widely accepted. And so this is another good reason why you need to have good lab notes, because then someone else can take your work and advocate for you for over a decade after you're dead. In terms of what you need to know that Avogadro's law links volume and the amount of substance of a gas. Just as a note, the thermal physics does have a required practical in it. It's technically 2 practicals, but it's listed as 1 required practical. One is investigating Boyle's law and the other one is investigating Charles's law. Obviously we can't really do those through a video. So we had a look at some of our ideal gases and we came up with 3 relationships. Boyle's law, pressure is inversely proportional to volume. Charles's law, volume is proportional to temperature, and Avogadro's law, volume is proportional to the amount of substance in the gas. So I'd like you to take a moment and try to combine those three laws into an ideal gas law. Pause the video now. You should end up getting that pressure times volume is proportional to the amount of substance times temperature. Pause the video if you need to think about this. How do we make that an equal sign as opposed to just proportional? We can use a constant. Now these constants are determined experimentally. So you have the Boltzmann constant K of 1.38 times 10 to the minus 23 joules per Kelvin, and the molar gas constant R of 8.31 joules per Kelvin per mole. They're both given on your data sheet, so you don't need to memorize them. And both forms of the ideal gas law are given on your data sheet, so you don't need to memorize those either. But do be careful about which one you want to use. It's very easy to get the definitions of lowercase n and capital N mixed up. So some ways to remember which n is which, or what to use with which constant. You can check the units. So does a unit of moles work with the units of the constant that you have? If you remember what the capital N and the lowercase n are, you can remember that only one lowercase on the left hand side. So the lowercase n goes with the capital R, the capital case N goes with the lowercase k. Or you can remember based off what they're called. So the molar gas constant, which is R, goes with the number of moles. Alright, so our key concepts from this video. The gas laws were determined experimentally. So the three gas laws are Boyle's law, pressure is inversely proportional to volume, Charles's law, volume is proportional to temperature, and Avogadro's law, volume is proportional to the amount of substance in the gas. These can be combined into an empirical ideal gas law, and there's two forms of that ideal gas law. And those forms are PV equals nRT or PV equals nKT. For both of these forms, P is pressure in pascals, V is volume in cubic meters, and T is temperature in Kelvin. And we need to be careful with units. If we're converting that volume, 1 million cubic centimeters is 1 cubic meter, and that temperature has to be in its absolute form of Kelvin and not degrees Celsius. For PV equals nRT, that little n is the number of moles and R is the molar gas constant. We can remember that these two go together by linking moles with the molar gas constant, or by taking a look at units in the fact that the molar gas constant has a per mole and the number of moles when multiplied cancels out that bit of unit. Whereas the capital N in PV equals nKT is the number of particles and K is the Boltzmann constant. Notice that the Boltzmann constant just has units of joules per Kelvin, and it's multiplied by the number of particles, which is unitless. So capital NK and lower n R end up with the same units. And that's all for today. Have a fantastic day.